Thank you so much. So it's really an honor to be here at IPAM. It's actually my very first time here. And I'm going to tell you a little bit of what myself and some of my friends and collaborators have been working on in the last couple of years, very much at the intersection of sparsity and deep learning. And essentially, as a motivating example, I wanted to bring this issue of inverse problems with which I'm assuming many of the people here in the room are familiar with, where we are trying to estimate some underlying signal, some underlying image that has undergone some sort of degradation operation. And these are two very common examples, trying to infer what was behind an object that was removed, for example. But then there are other more challenging and perhaps interesting problems, like removing clutter from ultrasound imaging, or performing CT reconstruction, or performing super resolution of various kinds. And everybody here deals with these sort of problems, and we often come up with solutions, algorithmic solutions. And these algorithms, typically deep learning versions of these solutions, actually achieve very good outputs, and they give you a solution that looks very good. And we seldomly ask ourselves, why is it that we can actually find a pretty good solution to these problems that actually don't have a solution? Or rather, they have an infinite number of solutions. So how is it that we can actually come up with one that looks as we would expect it to look like? And I would argue that it is because all these algorithms recognize and can leverage some sort of intrinsic structure that it is present in all these types of information sources and images. And this structure can be characterized in a number of different ways. A very common one is through the formalism of a signal model. And this is a good idea because if you know if you have a model of what your good signals should look like, then you can formulate this problem as an optimization problem where you're minimizing some error term, where you're essentially looking for an estimate that's not too far from the input that you were given, while at the same time being likely under some prior. So having these nice properties that you would expect these signals to have. If you look at the evolution of image models through time, 50, 60, 70 years ago, you would have expected, okay, natural images to have bounded energy. But, well, actually, this is better if you impose some smoothness, so low energy after some sort of transformation. And perhaps an L2 norm is not too good of an idea, so you could use a total variation, which is actually very close to the heart of IPAM. And then, well, you could also impose some unitary transformation and impose an L1 on the coefficients. So you're imposing sparseness on, for example, the wavelet coefficients. And then this was sort of generalized by this idea of sparse and redundant representations, which is basically what I'm going to be focusing my talk on. And of course, by no means this is an exhaustive list of image models. There is a plethora of them. No model is better than others. It's like siblings, right? Everybody's really good at doing one thing. And then what I would like to bring to your attention, or rather to question, is whether the fact that pretty much most of the applications, most of the state-of-the-art algorithms for image processing are implemented, or in terms of deep learning models, whether deep learning constitutes such new version of image models. And perhaps we can revisit this question at the end. So I'm going to be talking at this intersection of sparsity and deep learning and neural networks. And so the whole idea of sparsity has been influencing the machine learning field for a number of years now. Perhaps the most iconic of that interaction was given in terms of sparse autoencoders, which I guess most of the people here are familiar with, where we basically try to train a decoder that takes the input, produces some codes, and then an encoder, and the decoder goes back to the image domain, and one typically enforces some sort of sparse promoting prior or sparsity promoting function on the codes computed by the encoder. Again, the literature on sparse autoencoders is very rich. These were perhaps two of the most the earliest and most representative works. And then the community realized that these sparse features were actually really useful, and so they started using them for feature extraction. Not only that, they realized that you could cascade these architectures, these sparse autoencoders, and create some sort of a hierarchy of sparse features. features that turned out to be very useful in terms of, for example, predictive power for image classification tasks, for instance. And again, this led to a very wide, a very rich variety of works dealing mainly with empirical results for supervised learning. And then this idea was taken further by the work of the convolutional networks by Fergus and Zeiler. And again, there is more and more modern versions of these autoencoders, like k-sparse autoencoders and unitary call, which basically they vary in what sort of sparsity is enforced in their representations, and there are many ways of doing that. But then, interestingly, the supervised learning framework has also influenced the sparse approximation community, and one representative example is a Lista work by Gregor and Lecan, where they showed that you can take this iterative soft thresholding algorithm, which is essentially a very robust power horse for doing sparse approximation, and you can unfold it, and then you can train these weights that would be otherwise determined. You can free them and train them in an adaptive way so as to approximate the solution of the original algorithm. And it turns out that if you do that, you can actually get very good approximations at a fraction of the iterations that it would have taken you had you gone with the original algorithm. And this went somewhat unnoticed in the beginning, but it has been receiving a lot of attention now from the ML community, basically to try to understand how is it and why and when supervised learning can actually aid these sort of sparse recovery algorithms. So what is this whole idea of sparse modeling? Well, it's a signal model, so it's essentially a set of model assumptions. And the assumption is that a natural signal, in this case this vector, can be well approximated by the linear combination of a few columns from this redundant matrix that we call dictionary, and these columns are atoms. And typically the problem is, well, I give you the dictionary, let's say, and you have your image. And the problem is, find a representation. Now, there's infinite number of these that are equally likely in principle. So we're going to try to find the simplest of them all, and we are going to measure complexity by the number of non-zeros that it has. So essentially, we are minimizing this L0 pseudo-norm that counts the number of non-zeros. And of course, this equality might be, this is an ideal setting, so in a more realistic case, you would actually minimize some approximation error with a sparsity constraint. And this error here would account for both noise that you have in your measurements, as well as model deviations, because models are not perfect. The problem is that this optimization problem here is NP-hard, is combinatorial. So instead of solving it exactly, we can actually resort to a whole variety of approximation algorithms. Some of them are greedy, so essentially you try to build the support of these vectors in some sort of a progressive way. Or you can relax the L0, which is it's non-convex and it's very discontinuous, to the L1 norm, which is it's a norm. And so this problem is now convex, so you can use your favorite convex optimization toolbox. Now, when dealing with images, however, the dimensions of these problems might be quite large, and so you cannot typically just run any interior point methods on this. And so we're going to be interested in algorithms that essentially just use matrix vector multiplications and entry-wise operations. And so you would like to do something like this, for example. You can take your measurements y and project it onto your atoms by multiplying by the transpose and then applying essentially the proximal of the L1, which is this soft thresholding function, which looks like this. And the output would be some rough estimation of what the sparse representation should be. And of course, it's not going to be exactly the one that generated your measurements, but it might be close enough. If you really want to compute the solution to this problem, then you should repeat that thresholding, and this is essentially a proximal gradient descent algorithm, and this is the ISTA, the iterative soft thresholding that Gregor and Lecan showed that you can actually relax in terms of a neural network that I talked in the previous slide. So these algorithms are in fact really good, and in some cases they find the solution that we are after, even though the solution is the solution of an NP-hard problem. And when we try to come up with guarantees, we need some sort of characterization of how hard this problem is. And that typically boils down to some sort of idea of how well posedness, how good is this dictionary for our means, for our objective. And there are many ways of characterizing the dictionary. This is one of them, the RIP, which essentially says, well, your matrix, remember, is redundant, right? So it's never going to be orthogonal. But at least I could hope that for sparse vectors, so when I'm multiplying vectors that have only S number of non-zeros, well, those combination of atoms will behave sort of like an orthogonal matrix. And so you're asking that the deviation of the norm is bounded by this constant here, which we call restricted isometry property. This is a very useful definition, but it's also hard to compute the RIP. So a more practical measure is this sense of mutual coherence, which essentially quantifies how correlated two atoms are in your dictionary. Again, if the dictionary was orthogonal, this would be 0. In the redundant case, it will not. It will be strictly greater than 0, and less than 1, up to 1. And why are sparse representations useful? Well, just to give you a very intuitive motivation of why you would like your representations to have, your signals to have a sparse representation, is because imagine you have measurements that have been, so your measurements are d gamma, gamma sparse, and they have been contaminated with Gaussian noise of power, let's say, sigma squared. Well, if you are to retrieve gamma, and this is an oracle estimator, but it serves the purpose of the example, this error in estimating gamma, it can be shown that it's going to be bounded by roughly sigma squared times the cardinality of your representation. And if this cardinality is much lower than n, which is the ambient dimension of your signal, then you have a very strong denoising effect. So this is roughly why you would like your signals to have some sort of sparse representation. Okay. Everything that I've described so far is actually called a synthesis sparse model. Why? Well, because you take some sparse vector and you multiply it by your dictionary, and that multiplication process synthesizes your signal. An alternative model is that of analysis sparsity, where now your signal X is not sparse, but it can be made sparse by multiplying it by an analysis operator, which analyzes your signal into a bunch of coefficients, and you would like these coefficients to have as many zeros as possible. And just like before, this problem is a very hard problem, and you can devise all sort of approximation algorithms, and there's kind of like a parallel story for these models just as well. And I want you to just keep this in mind, because a little bit further in the talk we're going to actually combine both of them. So what happens in the convolutional setting? Well, in convolutional sparse modeling, it's a sparse model just like we saw before, with the difference that now the dimensions are huge. So we are not modeling little patches, but rather complete images. And the dictionary is not just an unrestricted redundant matrix, but rather is restricted to being this set of convolutional filters. So basically, each column has a low-dimensional local filter at every single position, and then the representations are given by the coefficients multiplying these convolutional filters. Now, it turns out that the L0 norm as a measure of sparseness is not really such a good idea in this convolutional setting. And the reason being that when you look at the bounds that you can obtain for example, the uniqueness of sparse solutions or the stability of these solutions in terms of the L0 norm, they don't scale with the global dimension of the signal. They scale with the local dimension of the filters. So basically, they're pretty useless. So what you want to do instead is redefine the way you measure sparsity. And one way of doing this is by formalizing this zero infinity norm, which essentially just counts the number of non-zeros in each of these stripe vectors. And these stripe vectors are the ones that code for this shift invariant local dictionary that produces that patch, and every single patch. And so you count the number of non-zeros at every possible stripe, and then you report the maximum. So it's kind of like a sense of density as opposed to that of cardinality. And so the way to go about this in terms of a pursuit is minimizing a reconstruction error subject to a constraint on the zero infinity norm. And interestingly, we can still use the L1 norm as a relaxation for the zero infinity norm. And what I mean by that is that just like it was shown that the solution of the L1 under certain conditions recovers the solution of the L0 problem, so the L1 recovers the solution to this zero infinity problem here, which is quite handy because we're going to be using these relaxations a lot. Okay. So far so good. We have that y is d1 gamma 1. Now, the gamma 1 might be interpreted as yet another signal for which we can impose a similar model. And so we can say that also gamma 1 will have a sparse representation in terms of another convolutional dictionary D2 and be also sparse. And this might sound a little bit weird, but in fact this sort of decomposition is again very natural. And what we are saying is, well, we can have, for example, a gamma 3, which is very sparse, and then you multiply by a convolutional dictionary and you get a sparse gamma 2. You multiply that one by a dictionary D2, and you do this over and over again, and then you multiply all of them together and you get an approximation x hat, which would be an approximation for your signal y. And this is not a cartoon. This is in fact the real decompositions that we get if one uses these sort of convolutional dictionaries, 4 digits, right? So D1 is essentially a bunch of little local filters. D2, which in this case is sparse for other reasons, D2 essentially gathers a small combination of those local filters in D1 and creates slightly more complex entities that we call molecules because they combine atoms. And then D3 does the same thing for D1 and D2, and it creates these now more complex entities that reflect digits because, of course, that's what they were trained on. Now, of course, I'm not telling you how to find these dictionaries yet. I'm not even telling you how to find the representations. But let's try to formalize what that problem of finding these representations would look like. Very generally, what we would like to do is find a set of gammas so that, let's say, D1 gamma 1 approximates y, and gamma 1 is approximated by D2 gamma 2, and all through L layers. And all of these have sparsity constraints on them, again in the zero infinity sense because we're in the convolutional setting. So this is, it seems like even a more complicated problem. So let's take just a minimalistic approach, and let's say, well, let's use that very rough solver, very rough approximation algorithm of the thresholding to estimate gamma 1. So you take y, you multiply by D1 transpose, you apply this thresholding, and you get your estimate. And again, this thresholding function, if you're using the L1 as a surrogate for the L0 infinity, would be a soft threshold. And let's assume also that these coefficients are also non-negative, which is perfectly reasonable in a generative model assumption. So the threshold that you would apply would actually be a non-negative threshold, which looks like this. And then under some conditions, this approximation might actually be quite good. And so you can envision using that one to estimate gamma 2, and you can cascade these down through L layers. And then the very nice observation that Vardan and Yaniv did in a couple of years back was to see that these expressions can be equivalently written in terms of ReLU, which is just a non-negative projection, and a bias, which is essentially the threshold of the soft thresholding function. And so what this means is that one can understand the forward pass in a convolutional network, which is essentially push your input through this sequence of affine transformations and ReLU nonlinearities, as a very coarse pursuit algorithm under this multi-layer generative multi-layer assumption. So this far is just an observation, but the nice thing about this is that then you can go and resort to the vast literature on sparse approximations and bring them to the realm of neural networks. And so this is one such result by that work by Yaniv and Vardan, where they show that if these representations are sparse enough, all these gammas at every layer sparse enough, and under some incoherence properties of these dictionaries, this mu of di that you see here, then the forward pass will get you the correct supports of these representations gamma, which, by the way, these representations are nothing else than the activations in a neural network, okay? And they will be also not too far away from the ideal representations that gave you this signal. So on the one hand, this is great because for the first time, we know that under some conditions, the forward pass is actually stable. On the other hand, there are a few kind of like annoying issues about this. For example, these bounds actually become looser and looser the deeper you go into the network. You can resolve some of these issues by, for example, saying, well, if each layer in the forward pass, if each layer is essentially performing the first step of this proximal gradient descent, well, what if I just keep performing these updates? And so one could propose this multi-layer basis pursuit approach where you don't do just a thresholding, but rather you actually solve the entire basis pursuit problem. And you do that layer by layer. And this improves some of those limitations, but there are other problems that are still there. For example, how do I know that the solution that I find will satisfy all the model constraints that I have? How do I know, how do I sample from this multi-layer model? Is the model empty? How can we know that? And we keep adding constraints to our model in this multi-layer fashion, and we're making our generative process very restrictive. So what are we getting in return? What are the benefits of all these added extra constraints? And in the end of the day, of course, what we would like to do is end up with some practical benefits that will hopefully be inspired by these principles. And we will get to this at the end of the talk. So, moving a little bit forward in time, one can do this following observation. The signal that we get, which is D1 gamma 1, can also be written in terms of this effective dictionary for all layers. So D from 1 to L, which is just the product of all these intermediate convolutional dictionaries. It's just one big linear system. And also the requirements that gamma I minus 1 should be the I gamma I, but and they should also be sparse. But all these can also be written in terms of saying, well, the last representation will have to be sparse. And also all these intermediate ones, again, in terms of these effective dictionaries, will also be sparse. And if this is your model definition, then the pursuit that you should carry out should be posed in this way. You're minimizing an L2 with these sparsity constraints on the innermost representation gamma L, and at the same time you're imposing an analysis sparse prior on this gamma L representation. Namely, you want gamma L not only to be sparse, but also to be sparse after you multiply it with these operators. And this gives us a very particular coupling of these synthesis and analysis sparse priors. Okay, so that's kind of cool, but so what? What do you get out of this? So if you exploit this, you actually can get a lot. And this is a demonstration of this for a 2-layer case. So here we have just 2 dictionaries. Gamma 2 is sparse, and gamma 2 also produces zeros in gamma 1. And those zeros have been bunched, located here at the bottom. Okay, so all these entries are 0. And this is useful because, again, revisiting the example of denoising that we did before, if you are to denoise your signal and try to find gamma L, if you ignore the fact that there are zeros here, then the bound becomes what we saw before, right? So S2, which is the cardinality of gamma 2, times the variance of the noise. But if you exploit the observation that gamma 2 should also generate zeros here, then these bounds can be essentially improved by a factor of the rank of these little matrix here. And intuitively, don't worry if this seems a little bit too complicated. At an intuitive level, this is happening because now we are adding a lot more constraints to our representations gamma 2. Gamma 2 now doesn't have just S2 degrees of freedom because it's restricted to live in a particular subspace spanned by this phi matrix in order to generate zeros here. So these extra constraints reduce the degrees of freedom of the problem, making this estimation better. That's essentially what's happening. And you can use the similar ideas to apply, for example, to develop stability guarantees and many other such results. This is essentially just giving you a gist of the type of results that one can get. Okay, so this is cool, but then, it seems that we are getting further from convolutional neural networks. So how do you go back to actual algorithms? And we are left with kind of like a nice analytical problem, but it seems kind of cumbersome because we have these nested L0 constraints, and some of them think synthesis, some of them think analysis. So what we're going to do is actually something very natural, which is just relaxing all these L0 norms to L1s. So we have the L1 on the last layer and an L1 on all the intermediate ones. And let's just look at a 2-layer model just to be precise. Okay, so this is the problem that we are interested in minimizing. And again, this is a multi-layer basis pursuit, basically because if this wasn't here, then this would be just a lasso, a basis pursuit problem. But now this has an extra level of complexity because of this non-smooth term. And if you're familiar, by the way, with the analysis lasso or robust sparse analysis regression, this is very much related to some of those other works. But a particularity of this formulation is this coupling between both synthesis and analysis operators. So that's what we are going to try to leverage to come up with efficient solvers. So we have this general function. F is smooth and convex, and G1 and G2 are convex but possibly non-smooth. We would like to do ISTA, right? But we can't, because for that we will need to compute the proximal of the sum of these two non-smooth terms, and that is in principle complicated. So we're going to try to do something else. Let's look at H as the sum of these two functions. And what we want to do is compute the prox of something over G2, because G2 is an L1, so this is easy. We know how to do. This is going to end up being a shrinkage. Great. Here, we should have some sort of a gradient step. But then H is non-smooth, so we could not use the gradient. We could use the subdifferential maybe, but that would likely be slow, and we would also have to fiddle with the step size, so we also don't want to do that. So instead, what we're going to do is, instead of the gradient, we're going to use the gradient mapping. The gradient mapping is actually, for those who might not know, is the difference between the variable and the prox grad of that variable. So it's gamma minus the prox of gamma minus the gradient of f. And this is actually very intuitive, because if you're familiar with ISTA, you can actually write ISTA as a gradient mapping descent algorithm. It's really nothing complicated. And this is sort of a generalization of a gradient, because actually this is 0 if and only if the gradient of those two is 0. But it is not really, in principle, the gradient of any function, any differentiable function. Okay, and we're going to do a change of variables. So instead of defining this for gamma 2, we're going to do it for gamma 1. Gamma 1 is just d2 gamma 2. And then we put everything together, and you end up with an algorithm that looks like this. And that looks rather complicated and ugly, but it turns out that this is actually very, very intuitive and easy to implement, because you can write this as an iterative algorithm that does a prox grad at every layer. Okay? And so because this is a multi-layer ISTA, it's also very natural to add a momentum term, and so this would turn this into a multi-layer FISTA, fast iterative soft thresholding algorithm. Okay, so this sounds, intuitive, but now what you should be asking is, well, okay, but you define everything in terms of these gradient mapping operators, and these are not really gradients, so what are you really converging to? Are you really minimizing the original function that you started with at all? And it turns out that you are not. So we spent some time looking at the convergence of these sort of algorithms. Interestingly, we couldn't find any previous works on proximal gradient mapping algorithms. So it was actually a very interesting pursuit. And so the sort of results that we have at the moment are basically saying that if your iterates are converging, then you can make your function converge, again, in function value, you can make your function arbitrarily close to the optimal. And there's a trade-off here with the step sizes at every layer, so that you can either converge very fast and be relatively far from the optimum, or if you decrease the step size, you can get arbitrarily close to the optimum of your original function, again in function value. And this is for ISTA, and then if you do this in FISTA, you actually get a very nice improvement in convergence rate. Now, this result says nothing about the rate of convergence, and we are pretty sure that those rates can be found, and this is ongoing work. So let's look at the algorithm one last time. This is it. Let's say that we start with by initializing all these representations with zeros. So these cancel out, and so you put all that together, you end up with that, and probably by now you're already recognizing that this is nothing else than the forward pass, because the shrinkage can be written in terms of ReLUs and biases. So great, so this says that the forward pass is actually already computing for us the first iteration of this multi-layer ISTA algorithm. Now, we don't have to stop at the first iteration. We can keep on going and compute the second and third, fourth, etc. So this gives us a way of generalizing the way that these innermost representations are computed by a neural network. And if you want to put this in a pictorial form, well, basically what we are doing is just computing representations with this recurrent network. And yes, you can unfold it, and it looks like that. So how can we test if these, sort of algorithm that think in terms of multi-layer sparsity and so on, whether it makes any sense in terms of a supervised learning problem? So to do that, we did this little experiment. Here we are going to minimize a supervised learning, cost. Let's say a classification loss of, loss to do classification. Let's say cross entropy. You get given labels hi, and we're going to have some classifier parameterized with parameters theta, and we're going to minimize those parameters. You can think of this as a linear classifier, and this classifier is going to be acting on some representations gamma star. Now, if these representations were just computed by the forward pass, we would just have a feed-forward neural network. But we're going to generalize this by saying that this gamma star should be the admin of this multi-layer basis pursuit problem. And solve this to optimality would be very hard, so what we're going to do instead is approximate the solution to this problem by the iterates of this multi-layer ISTA algorithm that I presented to you before. And once again, if k is equal to 1 for the multi-layer ISTA, then this whole problem implements nothing else than a feed-forward neural network that computes representations, applies a final classifier, computes the loss, backpropagates the loss. And then if k is greater than 1, we have this more sophisticated recurrent network that, by the way, still has exactly the same number of parameters, because the parameters here are the dictionaries and the biases, and they all remain the same no matter how many iterations you perform, clearly. So then you go out, you implement this in PyTorch, so thank you very much for the previous talk. And it turns out that when you do this, when you increase the knob on k, performance increases. And this is for CFAR, and you can see this for MNIST and SVHN as well. In blue here, you have the performance of this feed-forward CNN. And in orange, you have the performance of these multi-layer ISTA for a number of unfoldings. And again, those two networks have exactly the same number of parameters. And you can do this for the multi-layer ISTA, you can do it for the multi-layer FISTA, or we have a version of this multi-layer LISTA, the learned work, essentially drawing inspiration from Gregor and Lecan as well, and they all perform about the same. You can also implement the layer basis pursuit idea, which I showed to you earlier today. But then again, the interesting question is the following. Okay, it seems that, you can improve performance by computing these representations a little bit more accurately without increasing the number of parameters. But in the end of the day, you're left with a network that is more, it's deeper, it's more complicated. So what would happen if I maintain this complicated architecture, but then I free all these parameters to be learned? Well, clearly, first, the number of parameters that should be tuned is going to, explode. It's going to be way, way bigger. But who knows? Maybe we will be able to obtain much, much better results. And if you do that, it turns out that performance doesn't really increase, if at all sometimes. And I should stress here, though, that learning, the optimization part, is actually done just with stochastic gradient descent and momentum. And there's no extra regularization. No extra regularization. We're not doing, we're not using dropout, and we are not using batch normalization, for example, which perhaps is the reason why these gigantic nets cannot really learn much better in this setting where all the parameters are free to be learned, and then there are just too many parameters in the problem. So that pretty much sums up what I had to tell you. If I had to mention in a very few sentences what I would like you to take from this is that this multi-layer sparse generative model is essentially a framework to develop analytical tools to come up with theoretical guarantees for different constructions in deep learning in such a way that different architectures can be understood and analyzed as approximating pursuit algorithms. And in particular, this multi-layer ISTA algorithm that I just showed you does perform better in practice. So it's quite at least satisfying for us to finally be able to take inspirations from all these analytical principles and put them down in an algorithm that does better empirically. So this is joint work with Yaniv Romano and Vardhan Papian, who are now at Stanford, and our PhD advisor, Miki Elad. And the last part was joint work with Aviad Avradam and Amir Beck from Tel Aviv University. So I'll be happy to take questions. Thank you.